So single qubit gates basically transform a qubit state from one state to another state. So we know that our qubits are represented as state vectors using the direct notation that we saw earlier. So basically, to transform one state vector to another state vector, we need to transform it using matrix multiplication. So single qubit gates are basically matrices that when multiplied to a qubit gives us a new qubit state. Just like in classical computing, we have classical gates that transform the classical bits from one state to another using Boolean logic, like AND gate, OR gate, and NOT gate. Similarly, in single qubit gates, our qubits are in form of vectors, which are transformed into new vectors by multiplying them with the particular matrix that we want to multiply them with. So this is how it works, that we have a get state and we want a new state, which is state dash. And for that, we have to basically multiply a gate to the state that we initially had. So let's say that our initial state is this column vector and the gate of transformation that we apply on it is this matrix. So we just have to multiply this gate to the state like this, and the new transformed state vector that we get because of this application of this gate is basically the new transform state. So that is how it works. If we have any gate, we just have to multiply it with our state to get the new state. And because right now we're talking about single qubit gates, that means that the number of qubits n is 1. So the length of the state vector is 2 because the formula is 2 to the power n and our n is 1. So the length of this vector is 2, where x essentially denotes the proportion of ket 0 and y that of ket 1. And the matrix that we apply on it is 2 by 2 by the same logic. So right now we're talking about single qubit gates. So all the matrices or the gates that we'll be talking about will be 2 by 2. So other thing is that if we have a ket state like this and we want to apply a lot of gates over a period of time and then find out our final state, then we just need to take our initial state and then multiply it with the gate that we applied on it first, then the next gate, until n, the number of gates we've applied in it. And when we do this multiplication in this particular order, then we get our final state. So let's look at our first gate of discussion, which is the X gate. And if you can see, our initial state is ket 0 and the final state is ket 1. And what is essentially happening is a 180-degree rotation about the x-axis. So whatever our initial state will be, it will be rotated by 180 degrees about the x-axis if we apply the X gate to it. So that is the effect of this particular gate in form of a visualization on the block sphere. But if we want to look at it as a matrix that will transform ket 0 to ket 1, then this is the matrix that does this job of a 180-degree rotation about the x-axis, which transforms our ket 0 state to ket 1 and our ket 1 to ket 0 state, which we can observe by opening the multiplication into multiple steps. So when we apply the X gate on ket 0, we do indeed get ket 1. And similarly, on application of X gate on ket 1, we get ket 0. So basically, our states are getting flipped. If we had ket 0, we are getting ket 1. And if we had 1, we are getting ket 0. So therefore, this gate is also known as quantum bit flip because it flips our state. It flips the state from the state at which it is to a diametrically opposite state, therefore the name. So if you want to implement X gate on Qiskit, then we simply need to create a quantum circuit with just one quantum register because we're talking about single qubit gates. Therefore, we initiate a variable Q, which is one quantum register, which is defined by this parameter 1 over here. And then we take Q as a parameter of a quantum circuit and get a quantum circuit with just one single qubit and apply the X gate on that qubit using this function of X and this parameter that implies which qubit of the quantum circuit should be applied with the X gate. And then it is displayed using this command and something like this that we've seen earlier as well, that we have Q0 as our initial quantum state. We apply X gate, which is a matrix on it, and get a new state. Now, two properties about gates that we should know are Hermitian and unitary. And let's see what they are one by one. So if we have a gate, and if we take its conjugate transpose, and both of them are equal, then our gate is Hermitian. So conjugate over here means that the imaginary part of every element in this particular matrix has to change its sign. But we see that there is no imaginary part to any of the elements in this matrix, therefore no sign change. Then transpose is simple matrix transpose that we all know, in which the rows become the columns of our new matrix. And when we apply conjugate transpose to our X gate, we get the X gate back. Therefore, X gate is Hermitian. And when we take the product of X gate and its conjugate transpose, and if we get the identity matrix, then the X gate is unitary as well. And from matrix multiplication, we know that if we have a matrix X and we multiply it with another matrix and get identity matrix, then that other matrix is basically its inverse. So X dagger, or the X conjugate transpose, is the inverse of X. And we have already implied, because the X gate is Hermitian, it means that X dagger is same as X. So essentially X is the inverse of itself, which means that if we apply X twice in a row, then it means that nothing changed. Like if we apply X on get 0, then we get 1. And if we apply X gate again on it, we get 0 back. And that means nothing changed. So if X is applied twice, nothing happens to the qubit state that we had. Now we've understood what X gate does by looking at the rotation on the Bloch sphere. And that is how we define it. It's a 180-degree rotation about the x-axis. But we don't know how we actually got this matrix to transform our state vectors like the way we want them to, as we have defined them. So one really cool property about matrices are that if we know their eigenvectors and eigenvalues, we can find those matrices. So we have to basically find the matrix, the eigenvectors and the eigenvalues of our X matrix. So if you are not familiar with the concept of eigenvectors and values, then do watch the video mentioned in the description. It will be really helpful. But in simple terms, eigenvectors are those vectors that do not get rotated when multiplied by a particular matrix, and they can only be scaled. Their size can grow longer or shorter, but they cannot rotate from their position. So if we find this particular vector, then it will be the eigenvector of that matrix. So intuitively, let's just imagine that we're having a 180-degree rotation about the x-axis, then which qubit state will not get rotated? And it's obvious that the qubit state would be one which is aligned to the x-axis. That is the positive and the negative direction of the x-axis. A rotation about the x-axis will not affect the position of the x-axis itself or any other qubit on the x-axis. Therefore, the positive direction of x, which represents get plus, and the negative direction of x-axis, which is get minus, are unaffected by the rotation about x-axis. Therefore, they are the eigenvectors of X matrix. So this we have just found out intuitively from our definition of the X matrix. And therefore, from the eigenvectors that we've got, we can find the X matrix that we want. But let's just assume that we already know what X matrix is for a second to verify that these are the eigenvectors and values of the X matrix. So you can see if we apply X gate on get plus, we get plus back without any rotation. And it's just the same, no scaling as well. Therefore, the eigenvalue for ket plus is +1. And when we apply x gate on ket minus, we get ket minus back without any rotation, but with a negative sign because of the scaling. So the eigenvalue is -1. And this is the result. Ket plus is the eigenstate with +1 eigenvalue, and ket minus is an eigenstate with -1 eigenvalue. And these two equations that we got, we just need to take everything to the other side and get x on one side, and then just take the sum of this and get the expression to find the x matrix, which is this. And if we take a ket from one side to the other, it becomes the bra version of itself. And this is the expression for x matrix. Now we just need to put these values in here. And we already know these values to be this from our previous videos. And when we put these values and simplify our equation, we get something like this. And when we put the value of the state vector ket 0 and ket 1 and their bra versions into the equation and apply matrix multiplication and sum them up, we get the x matrix just as we expected it to be. We derived it from the definition of the x matrix or the x operation, which is 180-degree rotation about x-axis. Then we used our intuition to find the eigenvectors and the eigenvalues. And once we know those values, we can easily find the x matrix, which is this, that will do exactly same transformations on a state vector that we just saw on the block sphere. So just like that, we have another gate, Z gate, and it does the same thing, a 180-degree rotation about the Z axis. But if we know that in Qiskit, our initial state is that of ket 0. So if we apply a Z gate to ket 0, we will see no change. And this we've seen in previous videos as well, because ket 0 is the eigenvector of Z gate. Because it is aligned with the Z axis, therefore a rotation about Z axis will not affect it. So to be able to apply the Z gate, we first transformed our ket 0 to ket plus state. And for that, we use H gate or Hadamard gate, on which we'll talk about later. So after we apply the H gate and get ket plus, we are able to visualize the effect of Z gate, which is basically 180-degree rotation about Z axis. So to get this rotation in mathematic terms, we get this Z matrix. And from our intuition and from the definition of the Z matrix, we can find out or derive it, and we'll do it later on. So the transformation it does is basically transforming ket plus to ket minus and ket minus to ket plus, which we can see by multiplying those values, and the result is consistent with what is mentioned over here. And because this is changing the angle phi of the qubit with respect to x-axis, therefore the application of Z gate is also known as quantum phase flip. X gate was quantum bit flip and Z gate is quantum phase flip. So to implement it in Qiskit, we again need one qubit in a quantum circuit. So the first two steps remain the same. Our default state in Qiskit is that of ket 0. So we first have to transform it into ket plus to see effect of Z gate, because Z gate will have no effect on ket 0. So we apply H gate using dot H function, then we apply Z gate using dot Z function, and mentioning the qubit that we have to apply this Z gate on as the parameter, and then displaying it, we get this circuit. And this does exactly what we saw on the block sphere rotation. So the just like the X gate, Z gate is also Hermitian and unitary, which means that if we take the conjugate transpose of our Z gate, we again get our Z gate back. Therefore, it's Hermitian. And when we multiply these two together, we get the identity matrix. Therefore, it is unitary. And because Z dagger multiplied with Z gives us identity matrix, so Z dagger should be Z inverse as well. And because Z gate is Hermitian, we know that Z is equal to Z dagger. So essentially Z is the inverse of itself. So if we apply Z gate twice in a row, there will be no effect at all. So now we know what the Z matrix is, but if we did not know this matrix, we can still get this matrix, deriving it from the definition of the Z gate and finding its eigenvectors and eigenvalues, and then calculating the Z matrix. To know more about how we get matrices from the eigenvectors and eigenvalues, you can look at links mentioned in the description. So we know that the positive and the negative direction of the z-axis will not be affected by a rotation about the z-axis. So ket0 and ket1 are the eigenvectors of z-gate, and we can verify this by actually multiplying with the z-gate. We don't really have to do this. It's just for verification purposes because we really are finding out what z is. So we cannot use it in deriving itself. So this is just the verification part. And we see that when we apply z-gate on ket0, we get ket0 back with no rotation. And when we apply it on ket1, we get a negative sign. It is just scaling. Eigenvectors can be scaled by the matrix, but not rotated. So these are the eigenstates and their corresponding eigenvalues. We know that this is the equation we got from here. We take ket0 on the other side, it becomes bra self of itself. And the second equation, we take this on the other side, we get this with a negative sign representing the eigenvalue of ket1. And taking the sum of these two equations, we get the expression to find the Z matrix. And when we put the corresponding values in this expression, we find the Z matrix, just like the one we used before in all our mathematical operations. And it is aligned with the definition of Z-axis because we have essentially derived it from the definition. So everything is consistent till now. So we've looked at X gate, we've looked at Z gate. So next in line is Y gate. It does the same thing, but a 180-degree rotation about the Y axis. So essentially this is what it looks like, and its matrix is this. So when we apply this gate on ket0, we get ket1 multiplied to a scalar I. And when we apply this gate on ket1, we get ket0 with a multiplication factor of -1. So if we look at it carefully, the state of ket0 gives us ket1 and state of ket1 gives us ket0. And this is just like X gate. Therefore, quantum bit flip is happening over here. But there is one more thing. We get these scalars multiplied to our state vectors, I and -I, and these are an effect of the phase flip that we're seeing over here. So basically, Y gate is a combination of both X and Z gate. Therefore, X gate was quantum bit flip and Z gate was quantum phase flip, and Y is a mix of both, quantum bit phase flip. So we can make the circuit of it using Qiskit the same way like we did earlier. And to apply the Y gate, we use the .y function and specify the qubit on which we have to apply it. Then we check if it's Hermitian. So Hermitian, we take its conjugate transpose. Over here, we do have the negative part. So this, the negative parts change sign, but after taking the transpose, we again get back the Y matrix that we initially had. And because Y is equal to its conjugate matrix or the conjugate transpose matrix or the Y dagger, therefore it's Hermitian. And if we take the product of these two, we get identity matrix. Therefore, the two are unitary. And like we've established earlier, like X and Z gate, Y gate is the inverse of itself because it's both unitary and Hermitian. So if we apply Y gate twice in a row, there will be no effect on our initial qubit state. And if we have to now derive the Y gate from its definition of 180-degree rotation about the z-axis without actually knowing what the Y matrix is. So again, we just need to find its eigenvector and eigenvalues, which are basically in the positive and negative direction of y-axis, because these directions are coincidental and aligned or parallel to the y-axis, and therefore are not affected by a rotation about the y-axis. A rotation about the y-axis will be affected on only those qubits which are perpendicular to the y-axis. Therefore, we know the eigenvector and eigenstates of the Y gate, which are plus I and minus I ket. This is from intuition, and we're verifying it mathematically over here just to be sure, but we know that these two will give us the Y matrix. So we don't really need to know the Y matrix because we're finding it. So these are the eigenvectors and the eigenvalues. And following the similar process, we ultimately get the expression for Y gate. And when we put the values of the expressions used in this equation, then we simplify it, we get something like this, and ultimately we get our Y matrix as we want it to be and as is expected. And you can see that we've used get plus I and minus I, and earlier we'd used plus and minus states. So remembering this block sphere is essential. So if your concepts with blocks were not clear, then do watch our previous videos because they are very important to understand single qubit gates. So you should keep in mind that this is ket plus I, which is basically something like this, and negative ket I negative will be a minus sign over here. The state of ket plus is this, and that of ket minus will have a minus sign over here, and we have ket 0 and ket 1 like so. So this will be the sum up of this video, wherein we've talked about how single qubit gates work, and we've talked about 3 important gates, X, Y, and Z gates, which are basically 180-degree rotations about the axes that we're talking about in the particular gate. And these gates are also known as Pauli-X, Y, and Z gates. And I hope you understood what and how these gates work. And I hope you enjoyed.